Good morning. Welcome to the physics video lecture. Once again, we have Psci 168, video lecture 35. We're talking about electricity. I keep saying electricity and magnetism. We're not there at the magnetism yet. So we're just talking about electricity and power. And I'm going to do a little bit of household wiring today. Not too much. I'm going to save the magnetism for next time. And we need to talk magnetism in order to get into the whole subject of motors, transformers, transmission of power. Right now we're just taking it for granted. Okay? We're taking it for granted, talking about the power in the home. Okay? So let's call this household electricity. After we pull it all together, we'll do a summary of everything. But for now, I'm just describing everything in terms of our simple circuit. Okay? Despite the fact that we're already talking about, we're talking about alternating current. So instead of a battery, I'll draw this source here. It's a delta V. It's hooked up to a resistor R. We're going to have currents. We're going to be alternating. We still have the same formulas though. In order to understand the alternating current generation, etc., motors, we have to talk about magnetism. But for now, just the formulas for electricity. And basically what this resistor does is it gets hot. That's what it does. So all of our devices that produce heat, electrical devices that produce heat, light bulbs, the range, the heating coil in your hair dryer, that type of thing. The type of household electricity that runs a motor can also be dealt with here, but to understand it, we're going to need the magnetism. So what do we have? We have delta V, this alternating voltage. I'll just write alternating here. But same formulas, don't worry. Is 120 volts or 240 volts, right? We had that last time. And we still have our delta V equals Ri. That's Ohm's law, and we have the power law. I delta V, and there were two different forms of that we could use. Well, three forms. This is amps times volts. This is watts. This is what we're keeping an eye out for. And yeah, everything is just producing heat. So there's this tie-in to thermal physics, obvious tie-in to thermal physics that we're going to explore. I also mentioned that in addition to our device here producing heat, say the light bulb, the current in the wires actually also produces heat. This was the idealized circuit where the wires had no resistance and all the resistances in the resistor here, the device, but in reality the wires themselves can get hot. So for the power formula, for that reason, I'm going to write it in these three different ways. So first of all, we could call this the original definition, I times delta V, watts, amps, volts, okay? Or P equals I squared R. And these are equivalent in a way. Or P equals delta V squared divided by R. This one in particular I want to talk about, because say we were talking about the power being used by our device here. Okay. How about I circle it in red to indicate that it's getting hot, right? So there's our device. And there's our power rating. You'd say, good, there's my voltage, 120 volts, current, that's how many watts I'm using. But in fact, the wires have some resistance, so in reality they do. And then you would add up the power that's being dissipated. You'd say, well, it's power in the wires plus the device plus the other wire, okay? And in that case, you'd add this in. You'd say, okay, I've got current squared times the resistance of the wire and on both sides. So there would be more than one power contribution. This heat contribution here is really wasted energy that we're trying to avoid. Okay? But in some way it's unavoidable, and it's the kind of thing we want to minimize. Because it goes in as the square of the current, we want to transmit as much power as we can without having too much current. Okay, and the way to do that is going to be with high voltage, small current. So an analysis of these things really takes you a long ways. So now let's look at some examples. And we're going to set up a list of household items. Household items that use energy. And we want to figure out the current for them. So we'll make a list, say 1 through 10. This, by the way, is homework. So leave some room in your notes. And what you just want to find out is the power and the current. Okay. So here I'll set this up better. So power, current. And we're talking about the 120 volts. Okay. And say 1 through 10. Let's get a couple of these going. So first of all, 60-watt bulb. The LED bulbs that say 60-watt, light output on them, comparing them to a traditional light bulb, they're really only using about 10. Okay, but we're going to go with the 60-watt incandescent bulb. And then you can get a list here. Toaster, say microwave oven. Say, I don't know what you guys have, a curling iron. Maybe a fan, hair dryer. This one I think we're going to do together. This one's pretty important. Okay. But go ahead and put together a list of some appliances you have around the home. Check for what the power rating is, and then calculate the current. So what is the current there? It's P divided by delta V. I equals P divided by delta V. So for our 60-watt light bulb, for instance, example, I equals 60 watts, 120 volts. What do you know? 60 over 120, that's 1/2. 0.5 amperes. Remember the car battery was a 12-volt battery. We had a 5 ampere current. Here at home, we have a 0.5 amperes. So current, 0.5 amperes. And you want to go through this list. Now, I know that some of the most powerful hair dryers nowadays, I'm told, don't have one myself, that they use up to 1,600 watts. So let's use a major one. That's what they say, 1,600 watts. That's a powerful one. What is the current there? equals 1,600 watts divided by 120 volts. Okay. So this is quite a bit. 160 divided by 12, so that would be 120 would be 10, and then 15 amperes. Okay. But if yours doesn't have 1,600 watts, go ahead and look what it uses and go ahead and plug that in here. But here we have the 15 amperes. So we can go from small to a major appliance that uses quite a bit of electricity. By the way, there's a motor in this hair dryer, but it's using the least part of the energy. It's the heating coil in there that's producing the hot air that's really using all the power. Okay, but 15 amps is a lot. And so your homework is to, fill these in, whatever you have. If you can get 10 of them, that would be nice. And you'll know. And now we get to the question of, what about the wires when you start having a lot of current in there? Okay, 0.5 amps is not that much, 15 amps is a bit more. Okay. Then these wires can get hot. See, this power would be that 15 amps squared times whatever the resistance is. So this brings us to the question of circuit breakers. Circuit breakers. Now, the most basic kind is what's just called a fuse. And then the kind that you have at home now is a switch in the panel that switches off and on when the current is too high. So excessive current will do what's called tripping a circuit breaker. Trip breaker, put that in scare quotes. It'll switch it off, and then you have to go switch it back on, and hopefully you discover the problem. Now the fuse is good to talk about because it's a little object here, often clear with glass, and what happens inside the fuse is there's a metal there that gets hot enough to melt. When the metal melts, when the current's too high, the metal melts, and then it interrupts the circuit. Okay. The circuit breaker, we're just going to call it a breaker, works on magnetism, so we're not quite there yet. But it's always when there's an excessive current. So that brings us to the hair dryer. I know a lot of students tell me they've experienced that. Maybe with a roommate, they both plugged in the hair dryer at the same time, and the circuit breaker tripped and the circuit shut off. And we can actually see why. If we've got these 15 amps, 2 hair dryers would be 30 amperes, and the circuit breakers in the household wiring will be set for 15 or 20 amperes. Okay. So plug circuits, uh, 20 ampere maximum. So there's the explanation for when you plug in 2 hair dryers. Their current, if you had 2 weak ones where or smaller ones, where the total current is less than 20 amperes, then you'd be safe. Otherwise, you got to go to another circuit. Okay. So plug circuits have a 20 ampere max. The reason, of course, is these wires that are also running through your wall, you don't want them to get too hot, in which case, your house could burn. So yeah, that's the discussion of circuit breakers. And if you get some images of these things, or actually even go around in your own house and find the panel, open it up, and have a look at the breakers and what they control, that's a good thing to do. These days, typically the electrician will label the different breakers. They'll say kitchen, bathroom, lighting, plugs, and so forth. And you can actually go through the house and test them out, and see what controls what. The more modern the house, the more breakers say in the kitchen. Kitchen will just be loaded with them. Okay. Bedrooms, not so much. Okay. Let me consult the clock here. I really just have one good. Okay, fantastic. So that's that assignment. So we're talking about household wiring. I'll do a little more on that. This example was important. Basically what you're going to find, so let's go ahead and discuss the electrical panel. So the electrical panel in your house, it looks like this. It's got a little ring handle on it. You pull it open, and inside there, you've got some rows of circuit breakers, and they've got a switch, and there's going to be a label saying what they do. Okay. If it's not too old of a dwelling. So what we're going to have is plug circuits, 20 ampere. The A is for ampere. Light circuits, 15 ampere. And these are your 120 volt type of circuits. Then you're going to have 240 volt circuits, and I'll put here the dryer will probably be 240 volts if it's an electric dryer. The range, the heavy kitchen, most of the kitchen appliances will be 120, but the range will be 240. Air conditioner will be 240. So what I'm going to have here for homework as well is hunt these down in your house and see what's going on. Okay. Take a picture, make a little sketch, list what you have there. Depending on your house, you'll have different options, but see if your plug circuits are 20 amperes and the breaker will be labeled with 20 or 15. These here are often 30 or 40 ampere, but remember they're 30 or 40 times twice the voltage, so they have quite a bit more power. Okay. As we still have that formula here, right? The power is the current times the voltage, so your 240 volt circuits will have your 240 here and then the maximum current there, and that'll tell you the maximum wattage that these appliances can use. If you wanted to convert it to horsepower for some of these big things like the air conditioner, you'd say 1 horsepower is 746 watts. Okay? But we don't need that. Horsepower we don't really need. Okay? That's a 240 volts. So the homework here is just to look at it and see what you have and write it down. Maybe take a picture, especially if you can print something out of that situation. Now, the last thing I'm going to do today is another calculation concerning the heat, and then we'll kind of set up the scenario for the following lectures. Okay, so all of these things are running heating coils and they're running motors. The motors will use the same formulations, but we're not there at the motors yet. So we're really talking about heat, and that takes us back to heating water, so we can get some idea about we can actually just go back to our thermal physics and relate it to some of these devices here. So I'll leave those formulas up there. I'll erase this. So, heating water. And we're just going to relate our thermal physics to our electrical quantities here. Okay. So our example, say we put a pot here on a hot plate. You can draw a hot plate. So we put a pot on a hot plate here, and it's got water inside, and we want to heat that water up. Okay. Good. So bring 1 liter of tap water to a boil. So how much energy is required? How much power? Well, let's use it using a 1,000 watt heating element. Okay, so we're going to bring a liter of water, tap water, to a boil using a 1,000 watt heating element. So let's remember what we have here. We have Q equals mc delta T. That was the thermal energy. Okay. Question here is, how long does it take? How long does this take? And how much energy? How much energy, and we could even convert it to kilowatts, kilowatt hours. Okay. So here's what we have. We have Q equals mc delta T. We have power equals energy over time. So we're going to solve for the time. Okay, the time is equal to the energy over the power. So yeah, by now hopefully you feel good about these kind of algebraic maneuvers. Okay. If not, just take your time, figure it out. So that from power is energy over time, time equals energy over power. And this energy is our Q. Okay. So, having said that, let's just go ahead and delta T divided by the power. And we have 1 kilogram, 4186 joules, kilogram degrees Celsius. And then the delta T is the tap water, we'll say room temperature water. So 100 minus 20, so we'll have an 80 degrees Celsius for the delta T. And kilograms cancel, degrees Celsius cancel, so that's just the number of joules. And then the power is 1,000 joules per second. So that second, of course, ends up in the numerator here. So the answer is going to be in seconds. Can we estimate this? Let's just call this 4,000 times 80. So we have 4 times 10 to the third times 8 times 10 over 10 to the third. And that's going to be seconds. Okay, so this is an approximation. washed pot never boils, it'll probably take longer. Okay. But yeah, 4 times 10 to the third, 80. 10 to the third cancels already. 320. 320 seconds. That's approximately 5 minutes. Okay. That's greater than approximately 5 minutes. How many kilowatt hours is this, right? The joules is easy, it's just the numerator here. We can also convert it to kilowatt hours, that's what you're paying for, and then you can actually put a price in cents, and it would just be not many cents to heat that, to boil that water. So we can do any number of examples like this. Okay. Heating water is really the classic one. 320 seconds. And it's a little more, right? It's this here, and then there are losses and what have you, but 5 minutes, 6 minutes. 8 times 2. So let's see, that's a good example. Now, I was about to write homework for this, but I'll just keep working it with you. Now we want the, since the numerator is the joules, we want to convert it to kilowatt hours. So we have Q, or I'm calling it W now, but it is just the Q, the heat. But the energy was 320 or more times 1,000, right? Joules. Joules, okay. And then convert to kilowatt hours. Now, how do we do that? We just keep the numbers. In fact, I'm just going to 4.2 times 10 to the third. I'll be a little more accurate this time. Okay, about 4.2 times 10 to the third times 80. So that was the joules. 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. So if you convert that to kilowatt hours, you just divide this number, which is 32 times 10 to the 4, 3.2 times 10 to the 5, divided by 3.6 times 10 to the 6. So that's about 1/10 of a kilowatt hour. So it's going to cost you a couple cents, okay, to do that. Equals question mark. You should put that in your, you should pull out your calculator and figure these things out as well. Good. And you'll notice this is similar to calculations we've done before. We've actually done this before when we were draining the dam and talking about the power and energy in the dam. So that's what I'm going to finish with right now. Just in terms of setting the, we're getting a little cartoon for where we're headed here. So I'll call this next time. Let's just remember, we've got the dam here. We've got the water behind the dam. We've talked about hydropower, so we take it down the penstock to the powerhouse here, okay. And then we've got the lower level of water. Got that H. So up here we have potential energy. Okay. It's rushing through here. Here we're generating power in some enormous number of watts. So we have to draw our transmission lines. So these are towers that carry the power across the country, and now it's actually carrying it to our house. This is where we were. Okay, there's our house. This is where we were boiling our water. So we have potential energy, power, and then over here we're boiling water. So we got the power here as well. The question is, how are we getting the power from here to here? We're already confident that there's energy conservation, that we could transfer the energy from one place to the other. But the way that's done, we have the idea of wires transmitting power and energy already with our simple circuits. But the way the power is generated here needs the laws of electricity and magnetism. Okay. So what we're going to do next here, generators, motors, transformers. And for that we need the laws of magnetism and electricity. So these laws of electricity and magnetism. And there's some really interesting material there that we have enough time to cover. We really just have a handful of lectures, but we'll actually get through there pretty nicely. So laws of electricity and magnetism, the way they work together is just amazing. It won't be with batteries, okay? It's not some giant battery that helps you get the energy from one place to the other. So generation of electricity, we'll learn about magnetism in order to understand it. So that's what we're doing next. In fact, next time I'll start just with a discussion of magnets and magnetism, and by and by we'll get the connection between these two, and then we'll be in there. Good. See you guys next time.